this theorem right here, I know theta can only be between 0 and pi in terms of radians. If you want to add that. I put it on the formula sheet. Remember the formula sheet I handed out? I made a note of that. So if you just want to put a little note that angle there would have to be between 0 and 180 degrees, or between 0 and pi radians.
Can it be equal to 0 to pi?
Yes, it can. Yes, very good.
What was the question you would say?
It could have equal it. Because I said the word between, she wanted to know, is it inclusive? Can you use those endpoints?
Okay.
Like a closed bracket. And it's like, yes, it can. Yeah, you can go all the way from that. And that's for this one. I don't think it's going to be something that'll bug you, but, you know, we should be very specific. Hey, doesn't that look like that? The only thing, this didn't have a magnitude, did it? Cool. Awesome. Well then, if that's equal to this, this we can prove. Then this must be equal to the area of a parallelogram that occupies those two vectors. Oh, we'll prove this because that'll be a piece of cake. Now we have a theorem. So let's draw a picture. Now in a parallelogram, you know, opposite sides are parallel. It's a quadrilateral, but the opposite sides are parallel. How about let's call this vector A. And let's call that vector B. This is going to be a quick proof. Now in the magnitude of the cross product of two vectors A and B in some parallelogram, just like that, must mathematically equal the what?
Area.
The area inside the parallelogram. Now this is huge because that means in three-dimensional space we can determine like the area of some parallelogram way out there. Well, let's prove it. Well, to get this proof started, we need to know what the area of a parallelogram is. Anybody know it? What's the area of a parallelogram formula from geometry class?
You just multiply the same.
Close. It's base times height. That's all it is. The area of a parallelogram is base times height. What's the area of a triangle?
Half base.
Half base height. The area of a parallelogram is just base times height. So you and I, let's go in this picture. We're going to prove this. That this is, you know, actually true. Let's build a height right here. Just drop an altitude and make it 90 degrees. This is fun. It's a quick proof. There's my h. And I'm going to start out and run area of parallelogram equals b times h. But isn't b a vector?
Mm-hmm.
So and I'm going to put a magnitude on that b and put that area. So that means length of vector, right? Just so I'm talking about, the actual length of that vector. Remember when we put those bars on there? I'm talking about its magnitude, the length, right? So length of this vector times the h. H is just some height. I'm not making that a vector. That's just some height. All right, now, let's put an angle in here. How about right there? The angle between the two vectors. What can I substitute for h? Well, everyone, isn't this true? I'm doing some trigonometry here. What's the sine of theta?
Sine theta equals to h.
I'm going to write this up here. Sine of theta equals h
over
over the magnitude of the a vector?
Yep.
Opposite of our hypotenuse, 7 degree? Or so coto of the so. Isn't that true? So what can I substitute for that h?
Sine a. Sine
Oh, good.
theta a.
She goes, you could solve for h, multiply this on this side, and I can take this and what, everyone? Substitute, whoop, right there. And I think we've done the proof. What's the area of the parallelogram? Keep that magnitude of b. What replaces this h? A magnitude of a. And the
Sine theta.
sine of theta. Isn't that cool? That was a quick proof. It will always be equivalent to the area of the parallelogram. Yeah? They might need me to hit those shades. Is it coming up all right?
Yeah, it's coming out.
Yeah?
Mhm.
I always worry with the sun coming up and all that.
Yeah, sine is helpful.
Oh, good. So that's the area of parallelogram. Hey, so let's make a formula for area of a triangle. You said it's half base height, right? What's the area of any triangle that would be occupied by this? Well, I'll just take that answer and divide by what?
Half.
Because you'll see that everyone on the problem set. You're going to see that on the textbook questions. They'll go, I think more often than not, they don't actually are the parallelogram, they actually are the triangle. So you just take your answer. After you've crossed the vectors, get the magnitude, you divide by 2. Magnitude means the length of that vector, right? What's the area of a triangle? I do have one problem in the problem set, though, that actually gets the area of the parallelogram. I'm going to erase this. Now, there are application problems. We'll get to that in a second. I'll write them on the board. But it deals with torque. But before we get there, let's do some problems that deal with this. Okay? I mean, I'm looking at the problem set. Lots of problems in here that deal with this stuff. So, I see one. This is the first one. I'm just going to make, what I'm going to do is these are problems taken from the textbook. Problems in the problem set, just kind of mix them up a little bit. I see one about cross products. Well, let's find this. I cross J cross K. And that looks confusing. We're going to find this answer. Find I cross, let me get here. I cross J cross K. This always throws off students, everyone, because it's written in standard basis form. You've noticed all along, I prefer to write my vectors like this, don't I? In component form. What confuses students all the time when they read this, they go, I don't know what to do. It's because it's written in that standard basis form. So let's start out, like that I. What is I in component form?
X.
And make it three-dimensional. What's that value right there?
X, right?
There's a number in front of the I. They just don't write it. There's an invisible 1. That's what throws us off. You're like, oh, there's a 1 there. So the vector I is 1, and what are these?
1.
They're zeros.
Zeros, yep.
Like, let's draw it, everyone. Let's draw a picture so we can visualize vector I throughout this whole course. This is the x-axis. That's the y-axis. That's the z-axis. Now you can throw a vector anywhere, but let's say I threw it from the origin. Which way would it go? Because it's got to have a length of what?
1.
It has a length of 1, and would go right down the positive x-axis with it. I'll just draw right here. There's vector I. Just go down this axis, stop. There's I. It's got a length of 1. I mean, just so you can visualize it. I didn't have to draw it from the origin. I could have drew it anywhere in that, but it would go in the direction of the positive x-axis, have a length of 1. Where's vector J if you want to draw it? What's J?
0, 1, 1.
0, 1, and
0.
good. All right, very good. Now, if you want to draw a picture of it, where's vector J?
Y, right?
Yeah, I can go right there. There's J. How long is it?
1.
So aren't these unit vectors? Remember that word unit vector? They're unit vectors, yeah. So now you follow me, you go, that can be confusing, but once you see this, it's fine. Where's vector K?
0, right?
0. And what would vector K be?
0,
0, 0, 1. Oh, you wouldn't believe how many times that's gotten students. Like they turn in a final exam. I did well, but that I cross J cross K, I didn't know what to do there. And you're like, what? I was like, I thought that wasn't it. Once they see this, they're like, are you kidding me? I can do that.
So,
Hey, so let's find it.
So oh, yeah, go ahead.
You sure? All right, well, let's go through it. And when we're done, I'm going to see if people in class can see, is there a faster way to find this answer? All right, let's do I cross J. So what would be I cross J? Well, that would be, I'll make my matrix. What was vector I?
1, 0, 0.
J was 0, 1, 0. And one, if you want to put the I, J, K, you can. What is I cross J? We got to start there, right? This should go fast because there's zeros and ones.
1 goes to
Wipe that out. 0 minus 0 is?
0.
Boom. Do the second component, but don't forget to change the sign. 1 times 0 minus 0 times 0, change the sign.
0.
Someone go with this? I'm just doing AD minus BC. Negative 0 is 0. And how about the last component? See, I'm wiping out the third column. 1 times 1 minus 0 times 0.
1.
This is I cross J. So to finish out this problem, you and I got to take this vector, 0, 0, 1, that's I cross j, and cross it with, let me write this, what is k again?
0.
Now you should get a funny answer when you cross the same vector. We're going to discover it. What happens when you cross a vector by itself? You get a very, very interesting answer. We're going to discover it. Some of you probably already have an idea what the heck's going to happen when we now cross these two. What happens when you take a vector and you're crossing the same vector, because that's vector k and that was vector I cross j. You get the 0 vector. We'll get the 0 vector. Really, there's a name for it? The 0 vector. Where all three components are what? 0. Because look, 0 minus 0. 0 minus 0, change the sign, 0. 0 minus 0. Is that always going to happen when you have identical vectors and you cross them? So what's the answer to this? You can write it like this, or if you want, everyone, if you want to put the answer 0, just make sure it's a vector. You go like that. That's the 0 vector. 0. The book puts it in boldface print. I put a 0 on it. Now, that was fun, but I bet there's a faster way to do this. There's something called the right-hand rule. Remember I was doing the cross product of two vectors is always what? Perpendicular vector. Everyone got that? I'll hold this up. All right, so you don't have to slant it. Here's my plane, here's the vector there, and there's the vector there, and they're sitting in the plane. But the cross product's what? Always perpendicular?
Mm-hmm.
Yeah, but which way is it going? Is it going this way or is it going underneath? Well, there's something called the right-hand rule to help you determine the direction of the cross product. You go, let's do it. So what I'm going to do with this I cross j. So we did I cross j. You got to use your right hand. It's right-hand rule. All right, get the tips of your fingers on vector I. Okay, I got you. There's vector I. Want to see that I coming out? And I need you to curl towards vector j. So it'd be like this. So watch me do this. All right, here's vector I, and I'm going to curl towards j. Someone see that? I curl towards j. Whatever way my thumb's pointing is pointing in the direction of the cross product. So let's see this. So I'm starting with getting the tips of my fingers on vector I, and I'm curling towards what? Curling towards j. Which way is my thumb going?
Up.
So I cross j is going up. It's going up. But see, you might have dawned on that. You might have been like, you might have had a fast way to do this. You might have been like, I cross j, I should just get k. And then k cross k, because they're the same vectors, gives you what? So there is a quicker way to do that math problem that we see that. But see, it's better to do that first, do all the math. Now we can discover that. I cross j should just be k, right?
Yep.
And then k cross k, 0. Now I do want to give you a heads up. In the problem set, I have an I cross j cross j. I don't think that answer is 0. So, but you can do all the math. You can do it any way you want. If you want to use geometry, you can. That's a geometrical approach. But if you want to use the right-hand rule to figure out the answer, you probably can figure it out. You know? Like, all right, I cross j is what? I cross j is k. Hey, I'll draw another picture. And let's say I get a vector here, and I get a vector over here. And this is vector A. This is vector B. I got them right there. If I did A cross B, could you tell me something? Would the vector be coming out of this green board or into the wall? Man, you're quick. He's quick with the right-hand rule. That was good.
So like this way, A.
Yep, so I got to start with A with my what?
Right
Tips of
hand.
my fingers. And I got to curl towards what?
B.
B.
Okay, so it's
And
coming,
which way is my thumb pointing?
coming towards me.
Yeah. It's just weird. This would come out of the board, right? And what I'm going to write out, then what would B cross A be? It has to go in the opposite direction,
Yep.
so it's going where?
B. Like,
But it's weird when you try that, because when I'm trying to get my right hand, you're like, all right, how do I do that? Look, see this? See what I'm doing? B cross A. Does anyone see my thumb? B cross A, look at my thumb. It's going into the board. That's called the right-hand rule. All right. Well, good job with that. I wanted to do one like this. I want area of a parallelogram. Let's see. Well, we better make sure I got something plotted here. That's 1, 2. That's 2, 5. 4. Let me make a better picture of that, I apologize. 1, 2. 2, 1, 2, 3, 4, 5. Right there. I just want to do an area parallelogram. 1, 2, comma 2, comma 5. All right. Now I got a point over here. This is 4, comma 3. And to make that a parallelogram, what would my fourth point have to be? Let's see. Like this. So the next one would have to be at 5, comma what? 5, comma 6. So I'm going to plot 5, comma 6. Now there's other ways to get area of parallelograms to geometry. Area of a parallelogram is base times height, but can we do this with vectors? Now that we know about vectors, the area of a parallelogram has to be the magnitude of the what? The cross product of two vectors. Well, can you help me make vectors out of these? I've got 1, 2, 4, 3, 2, 5, 5, 6. These aren't vectors, but these are points, right? Let's make a vector right here. Now let's make a vector right there. Does that sound cool? We'll call this vector F. But how, I did this problem on purpose.
Keep minus tail, right?
There you go. It's like, how do we make vectors from points? I've only done it once. I did in the last class. We gotta do it again. You said tip minus tail, right?
Yeah.
So what would vector A be?
2 minus 1.
2 minus 1 is 1.
And the other one is 5 minus 2.
3. Now everyone, because I'm going to do a cross product, I know I'm going to do a cross product because I want to get the